All right, in this lesson, I want to talk about the idea of a basis. And the reason this is important is because in quantum mechanics we have a very familiar idea that any state, which I'll demonstrate here by a ket, but we could also just call it as a wave function, right, of position and time, say. We often write it as an infinite sum of basis kets. I'll say, well, I guess in this case I would say I. Basis kets multiplied by coefficients, right? These, and for wave functions it would be exactly the same construction, I equals 0 to infinity of some coefficient and some set of basis kets. I guess I would call them, say, psi I, right? And this is a very habitual thing for us in quantum mechanics. We just derive these basis kets from the eigenstates of Hermitian operators, right? And we assume that these eigenstates are, well, generally we assume that they're certainly linearly independent and that they span the vector space. Now, there's caveats to that, of course. There are some eigenkets that have multiple eigenkets that share the same eigenvalue. That can be further analyzed by other operators, but for right now, understanding that in our foundation lecture, we really haven't touched on exactly how we understand operators, and we're going to have a lot to say about that. This is essentially a mini course in functional analysis, where that's what it's all about. It's a lot about how operators behave. But understanding we haven't that, just going back to your basic quantum mechanics, you know that we live and die by these bases of states. Basis of the set of all possible states, which we call the Hilbert space. And that's where, a lot of this is intended to dig into is, okay, we're going to learn what the heck a Hilbert space is in gory detail in these lectures that I'm doing now. And that's going to put us on there's no other way to say it, an emotionally stronger foundation when we think about quantum mechanics, because instead of this sort of hand-waving idea where the books say, the following space is called a Hilbert space, and just trust us, it exists, which is a totally fine way to go. You can learn all quantum mechanics you need with that. But the idea here, and sort of the idea of all of the lectures that I try to do here in the Xylix project, is to just take a shot at starting to dig a little bit deeper. So we're going to talk about a basis, and we're going to learn actually a few pretty bizarre things today. Today's lecture, or in this lecture, we're actually going to discover that this is not even a basis in the fundamental sense of the word as understood by mathematicians. And that kind of starts peeling apart this important idea of why mathematicians were so offended by physicists in the early part of all this. And I'm not an expert on the history of quantum mechanics, but I've read the same textbooks you guys have read, I'm sure, where they constantly talk about how, or quote old mathematicians who kind of roll their eyes at things like the Dirac delta function, right? And they're like, what the heck are physicists doing? What do they think is going on here? And of course, this is part of the idea of how bases work in infinite dimensional vector spaces. They're very important, right? When you have CK, continuous eigenvalues, right? For, say, scattering states or states in the continuum. And we call this a basis too, right? So all of this kind of goes back to what were they thinking about how basis worked in linear algebra, and how do we get to this idea, and why is that idea actually a little bit unusual? So we're going to talk about that in this lecture. We start with the idea of linear independence. And linear independence sits on this statement here, that these vectors, right, these vectors phi 1, phi 2, all the way to phi n, are considered linearly independent. if the only way to make this expression true is if all the AI equal 0, right? If that's the only way to make this statement true, then these vectors are linearly independent. What's critical to see here is that this only makes sense. This concept, this definition of linear independence only makes sense for a finite number of basis vectors. If this was an infinite series, then saying that this is only true if A equals 0 it's not a solvable problem, and it doesn't mean much. And so the definition of linear independence is wrapped up in the idea that only a finite number of vectors can be confirmed as linearly independent. And this is really interesting because for a basis, we always say that a basis is, if nothing else, is a set of linearly independent vectors, and certainly a basis for an infinite dimensional vector space, right, must have an infinite number of basis elements. And clearly, the way we're playing the game in quantum mechanics is an arbitrary vector in a vector space must be understood as the sum of an infinite number of basis vectors, right? And this becomes a problem because this has to be a unique decomposition, and as we just said here, if you can't solve this equation for an infinite series, it really doesn't make sense to say that you can confirm that this is a unique decomposition of this vector in this basis. Now, mathematicians have evidently known about this and worried about this problem a lot, and they made it really clear that a basis for a vector space has to be such that any arbitrary vector in the space, right, any arbitrary vector must be decomposable into a finite sum. I guess this should be a 1, right? Let me erase it. A finite sum of basis vectors. The basis set could actually be infinite, but every vector in the space must be decomposable into a finite sum of basis vectors. Now, this still brings up the point as well, okay, I have this infinite collection of bases. You say mathematicians are okay with that, but how do you show that that infinite set is linearly independent? I mean, they have to be linearly independent, and you just said you can't prove that they're linearly independent. So what they've done is they've made the following determination. An infinite dimensional basis, the way they've said it is, an infinite set of vectors are linearly independent if every finite subset is linearly independent. And each finite subset's linear independence is verified through this expression here. So with that in mind, define a possible basis for an infinite dimensional vector space. There still is the requirement that every vector be decomposable into a finite number of basis elements. And this is not the way quantum mechanics does it. So clearly quantum mechanics is doing something different. But mathematicians insist on this, and this is called a Hamel basis. A Hamel basis is a basis whereby this statement is true for every vector in the vector space. And what's very, very interesting is that every vector space has a Hamel basis. And it's a very fascinating mathematical story, and I think we'll talk about it that's what the rest of this lecture will be about. We'll be understanding the sort of the mathematician's viewpoint of what a Hamel basis is and showing that every vector space has one. And then this will establish sort of the contradiction between what mathematicians view as a classic basis for a vector space and what is being done here in quantum mechanics and why they're different will be the topic of subsequent lectures. Let's begin with an easy example. The vector space of all polynomials over the real numbers, where meaning over the real numbers is what we intend to mean here is the scalars are real numbers. The polynomials are all expressions like this. Our sort of variable for the polynomial will be x. That set is a vector space because you can add two polynomials together and you get another polynomial, and you can multiply a polynomial by a real number and you'll get a polynomial, and every polynomial has an inverse and an additive inverse, and so it's ultimately a vector space. And there's a zero polynomial, right, an additive identity. So with that in mind, this is clearly an infinite dimensional vector space. To see that is that there's really no bound on n. N can be any number. So there's an infinite dimensional vector space, and an easy basis to pluck out of it is 1 x squared, x to the third power, etc., etc., etc. That's an easy basis, and it certainly is infinite dimensional. It also satisfies the rule of linear independence because if you take any subset of these, you can prove the linear independence. You could set up some equation like you just pick an arbitrary set of, say, 3. You go and you could create a1xn plus a2xm plus a3 x p equals 0, and you'll be able to show without much trouble that the only way that can be 0 is if a1, a2, and a3 are 0. And you can do this kind of thing for you can expand that for every possible finite subset. So this satisfies the idea of a basis. And what's interesting about this one is the Hamel basis. This is a Hamel basis also. And it's a Hamel basis because every vector, which is every element of this vector space, is obviously a finite. It's any polynomial has a highest term and then a finite number of terms below it, and therefore a finite number of these basis vectors will satisfy the will not satisfy, I guess, will be the decomposition of any arbitrary vector will clearly be done in a finite number of these, with a finite number of these basis vectors. And so this is an example of a good example of a Hamel basis, and it's probably one of the few examples that are really, really easy to find. We can consider a much more difficult example called L infinity. L infinity is the vector space of all real number sequences. Infinitely long real number sequences. So there's no end here. But any real number in any slot is okay. And such an object, it too, there's sort of an obvious set to nominate for a basis, right? You might, I think most people, if they were forced to come up with something right away, would say, okay, well, what about a basis like this? The first element is 1 with all zeros, right? And the second element is 0 with a 1 in the second slot, right? And then the ith element is a 1 in the ith slot with zeros everywhere else, right? And that's, that's a start, right? You might imagine that would be a good basis. And it certainly would be a good basis in the context of this idea, right? The problem is it's certainly not a Hamel basis, because if I just create the simple sequence 1, 1, 1, 1 with 1s in every slot, then if I call that vector psi, then psi is the infinite sum. I equals 1 to infinity, basically EI, right? And that has the downside of being an infinite sum, right? So that's not a Hamel basis. So to find a Hamel basis, I need to come up with something else in order to make this sum finite. So I might actually add that vector itself. I might actually say, okay, I'm going to create another basis vector. I'll add 1, 1, 1, and this will take care of this condition. And you might think that would work, and then somebody says, oh, wait a minute, I got an idea. I'm going to, really annoy you, and I'm going to make a new psi, and it's going to be 1, 2, 3, 4, etc., etc., etc. And now you're really back into this condition here where you're using these, because even if you included this one in this basis, you could also, you're going to have to correct it by using these guys, and then you actually also have the problem of not being unique, right? It's still not infinite, or it's still infinite, and it's not particularly unique, and all that's a mess. In fact, uniqueness is one of the reasons I think that they force this finite constraint. And it's worth some time thinking about how would you create a Hamel basis for this vector space. And as far as I know, nobody has the answer. Nobody knows how to create a Hamel basis for this vector space. Despite that, we know that a Hamel basis exists. And in fact, a Hamel basis is supposed to exist for every vector space. So let's have a look at why we know that. So the way we approach this proof is we begin with at least one. We begin with a set of at least one linearly independent vector. What we actually want is any set that contains linearly independent vectors. And this set could be finite or infinite as long as it fits the definition of linear independence. So if we called such a set, let's just say that it had one linearly independent, we would call it L1. And then we study, and so our vector space we're going to call V. That's the entire vector space, right? And it doesn't matter what it's over or what it is. As long as it's a vector space over some field F, we'll call the field F, and F could be the real numbers, the complex numbers, any field, right? So we have the vector space F, and then we're going to create a subset. L1 is a subset of V, and the property is that L1 contains entirely linearly independent vectors. And for the purposes of this proof, I'll just call the vectors by some Greek letter or something, just to make it a little cleaner. So once we have L1, and I should stress, L1 can be any set of linearly independent vectors. I've depicted it with one in it right now. But this L1 is really to indicate that it's the first of several sets we're going to make, not that it contains one vector. In fact, why don't I just go ahead and just, for the sake of I'll just put some dots in here to indicate that it's just a set of several vectors. So then I study the span of L1. And presumably the span of L1 will not be the entire set V. It could be, and if it is, then we're done. We've proven that V has a basis. But if it isn't, we have to take the next step. So I look at the span of L1, and then I pick out an element from V minus the span of L1. Sometimes it's written with a minus sign. Sometimes instead of a minus sign, mathematicians like to use a backward slash like this. But I think I'll just stick with the minus sign. So we know that any element in this set, this is a set now, this is a set of vectors that are clearly linearly independent from all of these vectors, right? Because this is the span, this is everything that's not in the span of L1. And the span of L1 is everything that's linearly dependent on L1. So I take one of those vectors and I create L2, where L2 equals L1 union this new vector, which I'll call, say, psi. And now I have the relationship that L1 is a subset of L2. And then I repeat the process and I create an L3 in exactly the same way. I study the span of L2, right? The span of L2, which, by the way, includes the span of L1. And then I find a vector that's left over after I subtract the span of L2 off of V, and then I create L3. And L3 is going to be created the same way. L3 is going to be L2 union. Let's see, I've used a phi, a psi, how about an eta, right? And then I can make the subset L3. And I can do this on and on and on. And I create what we call a chain. This is a chain of inclusion, where each set is a subset of the other set. Now, I could take this chain and I can create another set. I'll call it capital Omega, and that set is the union, or not, it's the union of all of these subsets, right? It's the union of all of these subsets of V. Right? And the chain could be infinitely long, right? If this is I mean, there's no guarantee that the chain will terminate. Maybe if it's finite dimensional space, it'll terminate, but if it's not, it won't terminate. But I can create a chain. I can terminate it if I want. If I don't, but a chain, I want to consider every possible chain ultimately, right? So many of those chains will terminate, many of those chains will not terminate. But each chain I'm going to identify independently somehow, right? And I'm going to speculate, well, I don't want to say speculate, I'm going to hypothesize, that's not a good word either. I'm going to establish the fact that in principle I can create every possible chain of linear independent elements, of vectors that are linearly independent in the vector space V. And, you know, it looks like if I tried to name each one, there'd be some sort of countable list. But clearly, this could be an uncountable list of all possible chains, and then all possible sets that are the union of the subsets that make the chain. So understand it's very, very important here to understand exactly what these things are. This is a subset of V. Right? L1 is all the Li's are a subset of V, and this is a set of subsets, right? So omega is not a subset of V. Omega is a set of subsets, which is often called a collection. I think you see a lot in mathematics, they'll say a collection. The collection sometimes means sets, but sometimes they like to use collection as a set of sets. And that's what we're dealing with here. We're dealing with a set of sets. So we also should consider, and what we'll need to understand, is that there is a set out there that we're going to call LL, script L, and that is the set of all subsets of the vector space containing linearly independent elements. And that's a whopping big set. And each of these sets are in it, right? Because that's a set that contains only linearly independent elements, and that's a set that only contains linearly independent elements, and so is that one. And if I had another chain, if I had a totally different chain, maybe I would call the other chain S1, subset of S2. I construct it in exactly the same way, right? S4, etc., etc. Then each of these is also a set that contains linearly independent elements. And all of those sets are in L sub L. L sub L contains every conceivable subset of V that contains linearly independent elements. So this is a pretty massive set. Even for a finite vector space, this would be an infinite set because, you know, if I had a basis, you know, just your standard basis for a finite vector space, like maybe the one we used in the What is a Tensor series, right? I guess in there I would use 0. Well, let's not worry about that. Right? So say I called the 4 basis vectors this. You know, that would be one set in L sub L, but another set would be just E1, and another set would just be E2, and then another set would be AE1, E2, E3, and E4, right? So every real number A, that's another independent set. Now, it turns out that that these guys are obviously related. In this particular case, this set would be related to this set, but that's not what matters. I'm looking at the set of all subsets of V containing linearly independent elements. So you can imagine how many there could be, and certainly it's a very hypothetical set. I don't want to think any. I don't want there's the way these sort of set theory things go is nobody actually does any of these things. They just stipulate that such a thing conceivably could exist. All right, so now this is our setup. Our setup was we had the vector space V. We had this set L sub L, which is all possible linear subsets of V that contain linearly independent elements. That's a huge set. And then we have a list of all the possible chains that were constructed using this technique here that we talked about before, right? All the possible chains where each one of these guys is a subset of the other. So that's a chain. So now, what do we do next? So now we could look at this set, and we're going to create something called a partial ordering. And a partial ordering is usually symbolized like this. And we would say that a partial ordering is we write down the set and the symbol that we're going to use for the partial ordering. Sometimes they use straight lines on the less than symbol. Sometimes it's these curly lines. That's what I'm trying to use, is the curly lines. A partial ordering is a way of comparing elements of the set and saying that one is greater than the other. So if I take two elements from this object, I'm taking, say I pull out a set L alpha and then a set L beta, I should be able to say one of two things. I should be able to say one of three things. Either L alpha is less than L beta, L alpha equals L beta if they're the same set, or you cannot compare. L alpha and L beta can't be compared at all. A partial ordering allows for this last possibility, that not every element of the set can be compared with every other element, but every element of the set can always be compared with itself, but it can't be compared with all the other elements necessarily. If it is comparable with another element, however, it's got to obey certain rules. So if L alpha is less than L beta, and if L beta is less than or equal to L gamma, then of course L alpha is expected to be less than or equal to L gamma. So it's got to be this transitive. And and there's a few other rules about the ordering that are important. This is a pretty obvious condition here. But it's called a partial ordering because not every element is necessarily comparable to each other. If every element is, so that's called a partial ordering. If every element is comparable to every other element, then we have what's called a total ordering. All right? So this is a partial ordering, and in principle we could have a total ordering. But we're building a partial ordering here. And what's our partial ordering going to be? Well, we are going to assert that we're going to say that L alpha is less than or equal to L beta if L alpha is a subset of L beta. This is inclusion. Our partial ordering is via inclusion. Inclusion. Not an H, that's an L. So clearly, what's important here is the reason it's clearly a partial ordering because it could easily be that L alpha and L beta do not have a superset-subset relationship. They may have some non-zero intersection, but they're not the same set, nor is one subset of the other. They could be totally disjoint as well. You could easily have two sets of linearly independent vectors that are not that are disjoint, right? You could have that. And in those cases, you could not make a comparison because the comparison depends on a subset-superset relationship. However, it's also true that any element in a chain does have a subset-superset relationship. So if any elements that are in one of these chains, or I guess I should say any two elements that are in one of these chains will have a subset-superset relationship. L1 has it with L2, L3, with L4, and forever up this chain. And any other chain that contains L1, right? L1 can be part of many different chains. Because remember, when we created L2, or in this case L3 from L2, we added a vector eta. We could have just chosen a different eta here and created L3 differently than we did when we chose eta. If we had chosen, say, gamma, right? Then L3 would not be the same L3. But L2 would be in two different chains. One chain where we chose eta and one chain where we chose gamma. So these sets are in many, many different chains. And they're always orderable with respect to any other set in any chain that they're a part of. So there's plenty of ordering to be done. Now, with that in mind, these sets, which are the collection of all of the sets in any given chain for every chain that's possible, these sets are totally ordered. These guys are totally ordered sets using this ordering rule, right? And now notice also what's an important thing to understand is that omega, right, is a subset of L sub L. Remember, I said before, omega is not a subset of V, right? Because omega is a set of sets, each of which contains linearly independent elements. Well, LL is the set of all sets that contain linearly independent elements. So omega is a subset of L. Therefore, omega inherits the ordering of L. L's a partially ordered set, and this is the ordering rule. Omega inherits that ordering rule, but on omega, or upsilon, or any of the sets that are intended to be listed here, it's now a total ordering. So these guys are totally ordered. Total ordering. Right, those are a total ordering. And then, but generally speaking, over here, it's a partial ordering. All right? All right, now let's look at these guys for a moment. That means all of them. When I talk about these guys, I mean all of the sets that are totally ordered because the elements of the set form a chain in L sub L. All right, so let's have a look at them. The important thing to note about this is that each one of these guys is bounded. And I'm going relatively quickly here because this is not intended to be a set theory course, but the idea of being bounded only makes sense in the concept of having an ordering. And being bounded means that there is an element. There's an element in L sub L, right? Call that element B omega, say, where B omega is greater than, I guess I have to make the symbol the other way. B omega is greater than Li for all I, right? For all the elements of that chain. So no matter what element of this chain you've got in omega, there is some element in L sub L that is bigger than every single one of them. And as a quick assurance of that, just take the union of all the L sub I. Take that massive union of all the L sub I for all I guess for all L sub I in omega, right? Just take that union, and that will be a bound, right? May not only be one, but that will be certainly a bound for it's basically a bound for every element in this set. Every element in omega will be bounded by the union of all the elements in omega. Now, if omega has an infinite number of elements, this union is perfectly well defined. It's still, in set theory, infinite unions are no problem whatsoever. Infinite intersections aren't even a problem in set theory. The only problem in set theory where infinite unions run into an issue is with topology. An infinite intersection runs into trouble in topology because an infinite intersection of open sets is not necessarily open, but that's a peculiarity for how we are creating the theory of topology. This is just pure set theory. This has nothing to do with topology, actually. And so an infinite union is really no problem. So even if for all L and I, for all L sub I in omega, even if that's an infinite collection, this infinite union is a perfectly sensible object. And whatever that perfectly sensible object it is guaranteed to be bigger than any individual element in that set. So the big point here is that every one of these sets is bounded in L sub L. All right, so now we're on the big step. Zorn's lemma. We are all completely set up to exploit Zorn's lemma. Zorn's lemma reads, if every totally ordered subset of a partially ordered set, S, has an upper bound, then S has a maximal element. So we're going to focus on Zorn's lemma here, and the partially ordered set we're talking about is going to be L sub L, right? That's our partially ordered set. So our partially ordered set, by the way, it's not V, it's not the vector space. It is the set, the partially ordered set of all subsets of V containing linearly independent elements, as we've defined it earlier, for both finite and infinite collections of linearly independent elements. So that's our partially ordered set. If every totally ordered subset, right? So that is what these guys are. These guys are every totally ordered subset. They were constructed out of these chains. Where did I do the chains? Out of these chains here, right? When we built these chains back here. Where I checked the span and added another element, created the next one, and created these chains, right? And then we took the sets of those chains and we put them together in an infinitely long list of totally ordered subsets. And we showed that each one, so these totally ordered subsets, I will, that's going to be omega and upsilon and, delta, whatever they are. There's an infinite number of them, of course. And they all are traceable from these chains, right? So we have every totally ordered subset, every partial ordered set has an upper bound. Well, that upper bound is what we called B omega a moment ago, right? B omega definitely is an upper bound for each of these things. The union of all of those guys, if nothing else, is an upper bound, and there's probably more than one upper bound. So if that's the case, we now know that this set has at least one maximal element. At least one maximal element. And a maximal element is an element that is not smaller than any other element, right? So what would a maximal element of this set be, right? This is saying we have a maximal element of our set of sets, or our set of subsets of V, our collection of subsets of V, where each element of each subset in the collection, or each element of the collection, is a set of linearly independent vectors. Well, that means there is a maximal, at least one maximal element. That means there's one maximal, there's a maximal set of independent vectors that is larger than any other set of independent vectors. And that guy is going to be our basis, right? So this is proving that there is a maximal collection. I'm always going to be some maximal collection of linearly independent vectors in this set that is a set of sets of independent vectors. So now it's important to understand that that guy is is going to be our basis. First of all, notice that it has to exist, right? If Zorn's lemma is true, and I guess I need to point out that Zorn's lemma, this all hinges on Zorn's lemma, and I'll talk a little bit about that at the end. But under elementary set theory notions, with the inclusion of Zorn's lemma, a maximal element for every vector space, regardless of dimensionality, exists. So how do we know that this guy is the basis? Well, let's say M is our maximal element. That's a maximal element of our set. Now consider the span of M. Now in principle, the span of M should be V, but let's say it's not. Then we can consider the set V minus the span of M, or in more, I guess, more precise set theoretic notation, it'd be something like V span of M, right, like that. So regardless, these both mean the same thing. I'm just using some set theory notes where I see them using this, and I just seem to remember using a minus sign. But I just don't want to confuse these with some kind of vector notation, so let's leave it with the set notation for now. Why not? If this, first of all, if this is the null set, then M is in fact a basis. The definition of a basis, of course, is that the span of M is equal to V, right? So if this set is non-empty, let's find a vector in that set. We'll call it X, right? So X is an element of V minus the span of M. Now, since M is our basis, and when I say basis, I mean Hamel basis, I know that I should be able to find a set of basis vectors. I'll call them phi I. And this is a finite set such that A1 phi 1 plus A2 phi 2 plus AN phi n, right, minus, I guess, AN plus 1 x equals 0. So now our attention is focused on this expression here. What we've done is we basically are now considering x to be linearly independent, perhaps. Well, if it was, for example, if an plus 1, if that equaled 0, right, say this term necessarily was 0, then we know all of these guys would have to be 0 because they are linearly independent, right? They are in the span of M, and we know that M is by definition a set of linearly independent vectors. So, and this is a finite set here, right? The finite collection. So these would have to be 0 if an plus 1 was 0. If an plus 1 was not equal to 0, if an plus 1 was not equal to 0 and this statement was true, then I could write x equals A1 over an plus 1 phi 1 plus A2 over an plus 1 phi 2 plus plus an over an plus 1 phi n, right? I could write that. But then x is, that if that's the case, then x is in the span of M, which we asserted it wasn't to begin with. So there's only two conditions here for this equation to be 0. An plus 1 equals 0, in which case x is linearly independent to these guys, which is a contradiction of how M was constructed, meaning that we could now find basically what I mean by that is I can take M union X, and that set, M union X, would be greater than M by inclusion, right? M would be a subset, or I guess M is a subset of M union union x, because x is linearly independent from everything from n, so I can just append it to it and make another element of L sub L. And that contradicts the maximality of M. Supposedly you can't do that. M is maximal by Zorn's lemma. So that's out. And then so A is not equal to 0. Well, if A is not equal to 0, then X is part of the span, which it's not allowed to be because we constructed it to be outside the span. Okay, so there's your proof that every vector space has a Hamel basis. Pretty interesting. So the only thing left to talk about is Zorn's lemma itself, right? So all I'm going to say about that is Zorn's lemma is directly traceable to the axiom of choice. The axiom of choice. And the axiom of choice and Zorn's lemma are, Zorn's lemma can be proven from the axiom of choice. I'm not going to do that proof. The axiom of choice is much easier to understand if you look it up and you sort of read what the axiom of choice is. It's basically saying that you can select an element of, if you have a collection of sets, you can select one element from every set, no matter what. And as long as they're all non-empty, presumably. So that's an easy axiom to understand. To getting from the axiom of choice to Zorn's lemma, it's a pretty good exercise in logic and set theory. But the point is that if you find the axiom of choice plausible, you should find Zorn's lemma as a direct consequence of it. It's an interesting idea because the axiom of choice is quite simple to sort of understand intuitively, but it leads to this idea through some step-by-step logic. So Zorn's lemma is generally accepted in the world of set theory, just as the axiom of choice often is. So there you have Hamel basis. So even this set here. So what's interesting about this is, what makes this so fundamental and fascinating is if you go back to this issue of the L infinity, the infinite number of sequences. This thing that I was talking about, there is a basis, an infinite basis that I guess, as far as I know, remains undiscovered. But it has to exist. There has to be some basis that will capture any sequence with a finite number of basis vectors. And so the thing to remember is this is where mathematicians really chew the fat over all this stuff. But notice where we have to go. We still have to go here. We still have to go to an idea where we have an infinite basis set. So that's going to be for some of our future lectures. That's going to get us into the foundations of quantum mechanics. And we're going to have to weave our way through a bit of functional analysis to get there. All right, see you next time.